All righty, folks. So we're down to our final video for AP Calculus AB. We will have covered every single topic. So last class, we talked about volume. And more specifically, we talked about rotational volume. So, and again, we'll let f of x be the function furthest away from our axis. And g of x be the function closest to the axis. And that axis is the axis we're rotating around. So we had two different types. First one we had was a vertical type of rotation. And this is when we rotated around a horizontal line. So two different types here as well. We have the one where we have our bounded region is greater than the axis. So in other words, bounded region is on top of the axis. And then we also had where the axis is greater than the bounded region. So we're just having a quick little review here to make sure that we are all kind of on the same page here. So bounded region is, or axis is above the bounded region. So now those formulas look like this. Our volume, if the axis is above, that was from A to B. All right. And we subtracted the axis from every single one of our functions. And again, the f of x is representing the function furthest from the axis of rotation. And then if the axis is greater, then that's going to be the thing that we would use first when we subtract. And then we also had our horizontal rotations. And that's where we rotate around a vertical line. So in this one, let's throw these up here. When we say the bounded region is greater than the axis, that means the bounded region is to the right. And if we say that the axis is the greater, it means it's to the right. So now these ones are going to be in terms of dy. So just a little review before we go and we take a look at our last type of volume, which is called cross-sectional volume. So this is our rotational volume. It involves the disk method if we have one function. If we have two functions and we're doing a bounded region like we are doing right here, this is the washer method. There's another one called the shell method, but we don't get into that in AB. Matter of fact, we don't get into it in BC either. All righty. Oh, I did X. I meant to do Y, friends. Sorry about that. So this is where we left off with last class, as we dealt with the washer method. And again, we're just doing a quick review since that's the big thing that we kind of want to make sure we take away. And the washer method could be rotated vertically or horizontally. Doesn't matter. We just need to make sure that we understand how everything kind of flows. So before we take a look at our last one, we'll do a real quick example of this just to make sure that we are all on the same page here. And that would be dy. So if I give you a quick example problem, again, just to really kind of make sure we hammer this home here. Let's see here, something like this. Write an expression for the volume. Right, don't solve. I don't really want you to go through all that. An expression for the volume of the region bounded by f of y equals y squared minus 4y and the y-axis when the bounded region is rotated around x equals -5 or around x equals 3. Add a quick little square in there real quick, that purple. There we go. All right, so this is kind of what we're dealing with here. We're going to take a little look-see around it. Now, to begin with, the y-axis, we do need to think briefly about what equation the y-axis is. That's the equation x equals 0. So, in other words, if I write myself a graph here, just so we can kind of see what's going on here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Well, first up, we're revolving around on the first one, around the line x equals -5. So that'd be right here. And on the second one, we're revolving around the line x equals 3. So this is part B, going around that line. So my two functions that I'm dealing with here, first up, we have the x-axis. Well, the x-axis, that's this line right here. And then I have the line, or the function, the non-function parabola, it's not a function, the non-function parabola of y squared minus 4y. So that's going to come up here. and turn around and come back here. So you can kind of see the area, the region that we're talking about here. So we're talking about this region right in here. So that's the area that we're going to evolve around. Now, we need to figure out where those two functions intersect. And so if you graph it, I mean, you can see it, but just to show where they intersect, if we set the two things equal to each other, so 0 equals y times y minus 4. So y equals 0 and y equals 4. So those are our bounds. We're looking for how close they are to our axis of symmetries when we're actually dealing with it. So last time I had you guys plug them into to the function when the axis of symmetry is in there. You actually don't have to do that. One of the things you can do if you want to just kind of keep it real clean is you just take your functions, pick a number between them. How about y equals 1? And you plug it into both. So if I plug 1 in for my first function, y squared minus 4y, so y squared minus 4y, I end up with -3. If I plug it into my other function, y of 1 equals 0, oh, there is no y, so that just is 0. And you can kind of see 0 is further away from -5 than -3 is. So when I rotate around -5, 0 will be the greater function. Like, on the contrary, when I rotate around the x equals 3, the green function, -3 is further away. So the parabola will be the greater function. So we can go ahead and write our functions here. So on part A, the volume, the bounded region is greater than the axis of rotation. So the bounded region functions will come first. We're going from 0 to 4. And I'm going to take the bigger function. So the bigger function is 0. And I'm going to subtract my axis. And then I'm going to subtract the smaller function from it. So that would be y squared minus 4y. And I'm going to subtract the axis from it. And the whole thing will be in regards to dy. So if I wanted to clean this up a little bit, I don't have to, but if I wanted to, I could. So 0 to 4. So I'm going to be squaring 3. That's my larger one. And then I'm also going to be squaring y squared minus 4y plus 3. There we go. And then if I'm going around the x equals 3, the axis is bigger than the bounded region, so the axis will come first. I made those -3, didn't I? Those should have been -5. Oops. I can fix that real quick. So that should have been 5 there. So we end up with 5 squared and 5 here. There we go. All right. Now 3 is bigger, so that means 3 is going to come first on the next one. So the axis will come first because the axis is more right, the greater of my bounded region. So it's going to be 3 minus the value that's furthest away. Well, -3 is furthest away from 3 than 0 is, so that means we use a parabola first. So y squared minus 4y. And we are going to square that. And I'm going to subtract 3. Then I have 0 as my second function. And I'll just clean that up again. Just get rid of some of those parentheses. Don't have too many. Kind of makes it a little confusing to look at. And again, I'm just asking you to write it. I'm not asking you to solve it. So this first one, we have 3 minus y squared plus 4y. We're going to square that whole thing. And we're going to then take this one here and go 3 squared. All right, so that was just a real quick review of rotational volume. Make sure we are on the same page here. But the next one we're going to be dealing with is something called cross-sectional volume. On cross-sectional volume, the volume, the region isn't revolved around an axis. Instead, it is a geometric shape stacked up from the lower bound to the upper bound, where the distance between the functions is the base of the geometric shape. So, in other words, let me see if I can't draw this a little bit. And again, I'm just going to pardon the drawing here. This isn't going to be the greatest drawing in the world. Let's take a graph, and I'm going to make my shapes perpendicular to the x-axis. So say I have a function that looks like this. Some sort of curve function, maybe. I don't know. Something like that. And maybe it's intersecting with some sort of line. So have some bounded region. It's bounded between those two shapes. What cross-sectional volume says is we're going to pretend that that distance there is the base of some geometric shape. So I'm making my base squares. Now, if I let the distance be the base, and notice, remember about squares, they're going to be the same length all the way around. So that means that it's going to go there, that goes there, and you start to build this idea of those geometric shapes. Make it a little bit bigger here. Something like that. Kind of ran out of room there, but it happens. And I guess I could have gone a little bit bigger. I can move that up a little bit. And so what happens here is, what I'm saying is, what if this volume is created from these stacked up figures from A to B, and you can kind of start to see the slices as they would come through. you can see all those infinite number of squares kind of stacked up to create like this little speaker-ish type system here. One of the ways to think about it would be like a deck of cards. A deck of card, you have a flat card, but if you, which has no volume, but if you start setting all the cards up on it, it starts to make a rectangular prism. That's kind of the idea that we're looking at. So the base of my square here, if you notice, first of all, the area of a square is whatever the base is squared. So whatever that length of that base is, that would be squared. Well, if I'm dealing with a bounded region, the length of that base is going to be whatever f of x is minus g of x. So if I'm dealing with it in terms of cross-sectional volume, it would be whatever the length of whatever that top function is minus the bottom function and squared. Notice, on cross-sectional volume, you subtract the functions first, then square them. Whereas before on the washer method, we squared each function and then we subtracted the difference. So that's the biggest difference that plays out here. What if these shapes were an isosceles right triangle? And again, I'm not going to try to go through and draw them all here. I mean, you don't want that. What if they were an isosceles right triangle? Isosceles right triangle. Well, on an isosceles right triangle, the area is 1/2 base times height. Well, but if it's isosceles, the base and the height are the same. So it's 1/2 base times base, or 1/2 base squared. So then in terms of integration, that would be from A to B. Notice the base squared is still the same thing. The only difference is now I'm going to be adding a coefficient in front of it. A constant in front of it. That, in this case, that constant would be 1/2. What if it was an equilateral triangle? Equilateral triangle. So an equilateral triangle, that would be √3/4 times the side length squared. Or that side length is the length of the base. So √3/4 times the base squared. Again, if you notice, all of it is going to be essentially the same exact integral. The only thing that's changing is the constant that is in front of it. So f of x minus g of x squared. What about if we made it a semicircle? Now, if it's a semicircle, that is the area of a semicircle is pi times the radius squared divided by 2. Well, if it's a radius, the radius is going to be half the length of the diameter. So if the distance in between my two functions is the diameter, then that's going to end up being whatever the base is, I'm going to have to take half of it. So the base divided by 2 squared all over 2. And if I were to clean that up, that would end up being pi over 8 times the base squared. I kind of see a pattern developing here, friends. Everything is going to be the base squared. It's just with cross-sectional volume, all that changes is what constant goes in front. And again, it's f of x minus g of x squared. Now we don't have an axis here, so we don't have to worry about trying to figure out is it the function minus axis or axis minus function, because there is none. Now, I say all that as far as just change the constant in front. Well, the one place where that does change is if we're dealing with a rectangle. On the rectangle, every once in a while, they'll give you a rectangle, and they basically, remember that a rectangle is base times height. And they always give you a height function. So they'll say like, let's let height be, and they'll give you some function equals h of x. So they'll give you maybe h of x is x plus 2 or something. So if that's the case, when you're dealing with, if they give you a rectangle, the volume changes just a little bit. Instead of having the distance squared, well, that's just the base. The height would be whatever that new function is that they give you. And we'll see an example of this here in a second. So notice we have a kind of a key difference here between rotational volume and cross-sectional volume. There is kind of a big difference here. Difference between rotational volume and cross-sectional volume. And that big difference is on a rotational volume. On rotational volume, we always take, where the constant is always pi, that's first, but what it ends up being is it's some function expression squared. Now I'm not counting the axis here. Function squared minus some function squared. If it's cross-sectional, then it's going to have some sort of constant in front, unless it's a square, in which case the constant is 1. But the main difference is that instead of function squared minus function squared, we are going to have function minus function squared, because that is the length of the base, or the distance between the two functions, which would be the base. That's the big difference between the two. Rotational, it's function squared minus function squared, whereas cross-sectional is function minus function squared. Function, yeah, function squared minus function squared. And cross-sectional, cross-sectional is going to be function minus function squared. It's the order. So that's the big difference. Rotation, square the two functions, then find the difference. Cross-section, subtract first, then square it. So let's try an example of this, and then we're going to go ahead. We'll try a couple examples, and we'll call it a day after that. And friends, we'll go back to next class and wrap this whole thing up here. And you would have finished calculus AB. All right. Determine the volume of a solid bounded by f of x equals x squared. Where's my caret button here? I'm going to use the caret button that's down there. It is. And the y-axis from x equals 0 to x equals 3, given the cross sections are perpendicular to the x-axis, and the cross sections are squares, equilateral triangles. All righty, so this is what we're going to play with here. So let's think about, first of all, the x-axis or the y-axis. If we're dealing with the y-axis, that's going to be the equation of y equals 0. Okay. And so we have y equals x squared and y equals 0, or f of x equals x squared and g of x equals 0. So the greater of the two functions, so if we're looking at it, the greater of the two functions is going to be x squared, and we're going out here from 0 to 3. So that's going to be our value that we're going to be doing our cross sections around. Let's start with squares. If you think about a square is the side length squared, or the base squared. There is no constant in front of it, so I'm not going to worry about putting constants in front of my function. So the volume is going to be the greater function. And so my greater function is the parabola minus my smaller function, which is 0. So if I'm dealing with the volume here, we're going from 0 to 3, and we have x squared squared so that means my volume then is going to be from 0 to 3 of x to the 4th dx. So then when we integrate that, x to the 4th is 1/5 x to the 5th from 0 to 3. And if I plug my values in there, I get 243 over 5. All right, so for the equilateral triangles, the area of an equilateral triangle is √3 over 4 times the side length squared, or in this case, the base squared. So I'm going to use that same setup, but I'm going to make my constant value √3 over 4. So equilateral √3 over 4 times, from 0 to 3, times x squared minus 0, bigger function minus a smaller function, squared. And I can kind of cut this one down a little bit here, down to √3 over 4. 0 to 3 of x to the 4th dx. So √3 over 4 x to the 5 times 1/5 so √3 over 4 times 243 over 5, which is the same thing as 243 √3 over 20. All right, so let's try one more of these here and give you guys a chance to deal with these yourselves here. First of all, before I make a mistake there, let's just erase that. There we are. Nope, that's what I want. There we go. Write an expression for each, but do not solve. Determine the volume of the solid formed by f of x equals the square root of x plus 1 and g of x equals negative 1/2 x minus 2. From x equals 0 to 3, given the cross-section are perpendicular to x-axis, and the cross-sections are squares, isosceles triangles, or our final one here, what if we made them rectangles with a height is given by the function h of x equals e times the square root of x. All right, let me throw in the stuff that's missing here. There we go. Let's see here. I had a square root here. I had a negative 1/2 x here. Minus 2 from x equals 0 to 3, and this was e to the x. All right, friends, go ahead and pause the video, and let's see what you guys can come up with. All right, friends, well, let's give this a shot here. It's our final problem on our final note for AP Calculus AB, and then we have finished the year. The rest of the time, we will be preparing for the AP test and clearing up our own stuff as well for our class. So let's see if we can do this here. If we're dealing with squares, the area of a square, we've already said is whatever the side length, in this case base, so it's the base squared. So if I'm dealing volume where the cross sections are squares, it's going to be my bigger function minus my smaller function. Now, friends, I got to figure out what the bigger function is. So if I plug, say, I don't know, plug 1 in to f, 1 plus 1, that's going to be equal to, let's do 2 just, I think 2 will be easier numbers. That'll be a positive square root of 3. If I plug 2 in for my g of x function, I get negative 1/2 times 2 minus 2, which would be a negative 3. So positive square root of 3 is greater than negative 3. So that means f of x is larger than my g of x. So that means I'm going to use the f of x function first. So from 0 to 3, and that would end up being f of x, so the square root of x plus 1, minus my g of x function, minus negative 1/2 x minus 2. And I'm going to square the entire thing. So I'm going to just clean this up just a little bit. Whoop. Like that. And I have the square root of x plus 1 plus 1/2 x plus 2 squared. So there's our squares. Our next up is our isosceles triangle. So the isosceles triangle that's going to be 1/2 the side length squared. So 1/2 times the base squared. So when I set up my volume, and again, I could just use what I had before, but if this was a separate problem, wouldn't have that luxury. So I do with the initial setup first, the square root of x plus 1 minus a negative 1/2 x minus 2 squared dx. So 1/2, and I'm just going to clean this up one last time here. And I have the square root of x plus 1 plus 1/2 x plus 2 squared. And my last one I have is a rectangle. So my rectangle is going to be the height times the base. So my volume, going from 0 to 3. Sometimes they give you the height as a number instead of a function, in which case you just put the constant number there. But in this case, I don't have that. Let's see here. So I have the height, h of x, times the base of my function, which is f of x, so the square root of x plus 1, minus the g of x function. And when we clean up the whole thing, we have from 0 to 3, h of x was e to the x times the square root of x plus 1 plus 1/2 x plus 2. Friends, it has been wonderful walking through AP Calculus AB with y'all, but we've reached that time where it's time to go ahead and call it a year. So I'll see you guys in class and we'll talk more about it. Take care.